All right, hello and welcome, you guys. Hope you're well. So today's session, it's really up to you guys how you guys want to take it forward. There are some things I would like to talk about, but again, there's just really few, and then we can go forward. Walaikum assalam. So I think because we've done a lot of the recent past papers, it's better that we have a look at some papers at random, and we try to sort of like look at how do you write responses to the question ones. Also, some people have been asking me for revisions regarding the uncertainty calculation, so I'll also be going over that. All right, so let's start at random. All right, so this particular paper is summer 2020, paper 52. Let's have a look. All right, again, all right, let's wait. I guess people are still joining. Let's wait till 6:05, then we'll start. People are still joining. Do you recommend any notes or book for P5 revision? Not really. Even if you've done like, I would say, even if you've done like 8 papers and you've really understood what goes on, so yeah, so you can do it. I don't really have any books as such in mind. Perhaps if you have a resource that you could share with me, I could give you like my seal of approval on it. But yeah, so I think this question, hmm. So yes, I guess something very similar to this we read recently. So first, let's have a look at question number 2, and then we should do question number 1. No, there is no such list of experiments for question number 1. It's going to be completely random. There is nothing in your question number 1 which is like theoretical. It's really random. Just a second, I guess I'm lagging a bit. Hmm. Yeah, so it's something which you are supposed to know. It's just at random. There are some experiments, and what you should know about them is, for some experiments, the safety points that you write, the additional detail points that you write, how do you get those? So that is something you should obviously know. So question number 2, a student investigates the discharge of a capacitor through a resistor as shown in 2.1. Student initially closes the switch, charges the capacitor. The switch is then opened and a stopwatch is started. The capacitor discharges through the resistor. At different times t, the current I is measured. It is suggested that I and t are related by this equation, right? And then this equation is given to us. Just a sec. Let me do this. That I have this here. Let me just open it here. List of apparatus, again, it's not like your practical paper, right? That you don't have to write about a list of apparatus. It's not like O-level ATPs. Uh, with the improvement in what you have to measure, you need to think about the different apparatus, and we'll be doing some of these. So just hold on for a while. Let's first start with question number 2. Question number 2. Yeah, so we were looking at this. So a graph is plotted of ln I versus t. Determine expressions for the gradient and the y-intercept. It itself tells you have to do ln, and it also makes sense because you have an e here. This becomes ln e over r of this entire thing, right? So here, if I write this, this is ln I. Basically, if I see here, I have a e over r term, and then I have the exponent to the negative thing term. So let's split this up using these log rules. So this is ln e over r, and there's the ln e to the negative t over rc, and you know ln e is a 1, so the power negative t over rc, this comes down. So this becomes negative t over rc. Again, this is not really difficult. You guys know how to do this. This is also something which was asked in a lot of recent P4s. Now, the next thing you need to identify is that if this is on your y, if this is on your x, so everything with the x, which is this 1 over rc, in fact, the negative 1 over rc, this is your gradient, and your y-intercept is ln e over r. All right. So for the next one, values of t and I are given in 2.1. You have t and you have I given, and you are supposed to calculate and record values of ln I in microamperes and include the absolute uncertainties in ln I. Now, the ln case is slightly strange if you guys know this. One reason that it's strange is the number of significant figures here in the I column becomes the number of decimal places in the ln column. So again, I don't have a calculator. Maybe you guys can tell me. So ln 46 turns out to be what? Negative 1 over rc was the gradient, because if this is your x, so by the straight line equation, whatever is with the x is m, it's a gradient, right? And this is basically rc, the y-intercept. Guys, what's ln 46? ln, all right, so ln 46 turns out to be 3 point what? 3.8286. But because this is going to be 2 decimal place now, I'll be writing this as 3.83. Right, so this is one thing that you have to take care of with the ln tables. Another thing with the ln tables is for finding the uncertainty, because you have I, you'll also be expected to find the uncertainty in ln I. You can't use a formula anymore, right? So what you have to use is what I call the max-min method. Basically, this value shows you that it could be 46 plus 2 as a max and 46 minus 2 as a min. So you basically have this value going from 44 all the way to 48. So for the uncertainty, what you can do is you can do the max value, ln 48, minus the average, the principal value, ln 46. Or what you could also do is you can do the average value minus the minimum value, right? And if you do these, both of these will turn out to be the same, right? So if you do ln 48 minus ln 46, they're not exactly going to be the same, but to the accuracy that you want to write it, they will be the same. So 48 and the ln of this. So 0.0425. So it's just going to be 0.041, right? That's how you fill out this entire table of the ln values. In a while, I'll also be going on to a question which is not ln. All right. Do you guys want me to go through this entire graph? Because I think we've had a lot of those on the platform as well. So I feel like you guys are pretty used to how this goes. I've also talked a lot about these in the live sessions, how you make the lines of best fit and the lines of worst fit and how you do the calculation, how do you give the units, uncertainties, all of this we've talked about, right? I just wanted to talk about the values a bit. All right. So anything else you want me to talk about related to question 2? Otherwise, we'll just go on to question number 1. It's up to you guys. I feel like this is the only stuff which is there in question number 2. Otherwise, I don't know how really to explain this. Because this is literally all there is to it. Error bars, all right. Let me explain in the context of a question that I've already done then. So this was a question, the recording of which is also available. I have a question. How did we determine the y-intercept? Look, Usman, I'll go through this once again in the context of this new equation. For example, if you look here, this says PV equals to yk theta plus z. This is the equation. It explicitly tells you that a graph is plotted of v on the y-axis, theta on the x-axis, right? Now, if you remember this straight line equation, so you know that on the left-hand side, you have y, which is all alone, right? So here your y is v, you first need to get your v all alone. So what I do is I write it like this, yk, and I expand it all. All right. And now I also know that theta is on the x-axis. So if I look here, again, just for visibility, let me write it out even more clearly. Let's write it like this. I'm going to write it in this way. I'm going to write it as yk over p times theta. Just so you see that this is the x here. So this right here is my y. This right here is my x. So if I write down here, this is my y, this is my x. What's the straight line equation? Mx plus c. So everything which is with the x is the m. Everything which is outside, which stands alone, that's my c. So this right here is my m. This right here is my c. All right. So that's how this works, always. Okay. So yeah, we were talking about error bars. Again, let's look at how the values are calculated here. So this was a case where the table of values was not ln, right? So we had to think about this. So h was given, theta was given. You are supposed to find v, and the relationship for finding v is also given, which is pi d square h over 4. And d is given here, and h is different for each value. So finding your v is not very difficult. Again, you have to give this in 10 to the negative 5. Again, to avoid myself in an exam setting to just get myself messed up with the standard form, I just substituted with the prefixes into the calculator. So for example, if this is milli, I substituted with 10 to the negative 3 into the calculator. This is also milli, I substituted with this into the calculator, and I let the calculator do its thing, right? And then I just write this value correct to 10 to the negative 5 with a prefix of 10 to the negative 5. So that's what I do. So that's how I get all of these values. And let me also just talk about the uncertainty calculation here a bit. So here, if you look at the relationship, because this is an algebraic relationship which defines how V is linked to these different quantities, I can basically talk about this in terms of percentage uncertainties. So the percentage uncertainty in V is twice the percentage uncertainty in D plus the percentage uncertainty in H. So now D is always this, right? So I found the percentage uncertainty in D and I multiplied it by 2. So that was always this value. And then to this, I only need to add the percentage uncertainty in H, which is going to be my percentage uncertainty in V. But that's going to be different each time out, right? So for example, in this case, what I've done is for this one, I've done 0.1 over 62.4 times 100 turns out to be 0.16%. I add to this value, this becomes my total percentage uncertainty in V, and then I just take this value of this thing, which gives me this absolute uncertainty, right? That's how I do it in this one. So yeah, that's how I fill out this entire table. Again, max min you can also use, but I generally don't prefer using it because it's a lot of work in the calculator. It also takes more time. Look, V is given by this relationship pi d square h over 4. If I look at percentage uncertainties, so V is basically made of the product of two things, and one of those two things is squared. So because it's squared, the percentage uncertainty will be multiplied by that value, right? So it's twice the percentage uncertainty of D plus the percentage uncertainty of H. D is always the same. So I've done this only one time where I found the percentage uncertainty in D. I multiplied it by 2, and this is what it turned out to be, right? And then for each value, if you look at it, the absolute uncertainty is the same. But because the principal values are different, the percentage uncertainties will also be different, right? So I need to calculate that every time. So for example, if I do this for the first one, 0.1 over 62.4 times 100 turns out to be this, right? So this is my 0.16 right here. Then I add both of these. This becomes my total percentage uncertainty in V. And because I found these principal values previously, I just take the percentage of this, and that gives me my absolute uncertainty. All right, does it make sense now? So then we had to plot this graph of V versus theta in degree Celsius, and you include error bars, obviously, always for the thing in which you find the percentage uncertainties. Daniel, look, once we have these, I have both of these, right? I add them. This is the percentage uncertainty in V. Now I found the principal value for V. So I just take that percentage, right? And that gives me the absolute uncertainty. That's what I do for all of these values. For the next one, it's 0.1 over 65.2 times 100, which is this. So this time out, I add 0.15 here. Again, I do all of this in my calculator, right? Otherwise, it's too hectic. Then whatever this turns out to be in my calculator, I just add a percentage sign in front of it and I multiply it by this value. And then I get this. All right, no worries. So yeah, so whatever you find uncertainties for is also what you will have to plot the error bars for. So because you found V, you would also have to do error bars for V. Now, the nice thing about this is in A2, you will be given your scale, so you don't need to think about that. Let's pick up any value at random. Let's do this one. Right, so theta is 35. So V is 3.99 plus or minus 0.03, right? So I am looking for 35 and 3.99 here. 35 is going to be right here. And 3.99, again, I just now need to read the scales. So there's a difference of 10. So each box is 0.01. So this is 3.99. Now, how do I come up with the error bars? Because I know each small box is 0.01, right? So 0.03 means I have to go 1, 2, 3 above. This is where I place my horizontal line here. And similarly, 1, 2, 3 below. This is where I place my lower, basically that lower horizontal line. And then I just make a small circle around this and I join to get my complete error bar, right? That's how I do it. Does this help with the plotting of error bars? Okay. Anything else here then? Plotting of best fit, worst fit lines. Always you do have to label what's your best fit, what's your worst fit. I could, yes, if the error was calculated for the X values, we would have to draw horizontal bars. It's sort of a rare case, but it does happen, right? So yeah, I was talking about this, that you always label your lines very clearly. This is my best fit, this is my worst fit. And then you guys also know how I do these calculations. Once you draw the lines, you know what the next steps are going to be: finding the gradient with its uncertainty, y-intercept with its uncertainty, and so on and so forth. And then at this point, which is always positioned at this same place in your paper, you then have to use the initial expressions that you found to find the values of these constants, right? The units thing is slightly tricky, so do make sure that you understand how that works. For example, in this case, y, if I look above to the question, so I don't know what y was, right? I don't know what it was. And another question, as I'll show you, I was given in the question what y was, right? Any constant. But here I rearrange this equation and I see y is gradient times p over k. The gradient always has units of whatever you have in y over whatever you have in x. So what you had on y was meter cube, and what you have on x is degree Celsius. So meter cube per degree Celsius. And then you have this in pascals, right? P, the pressure was in pascals. And K, the Boltzmann constant, you guys might identify this, was in joules per Kelvin. Now, you know from thermodynamics as well that if you have a temperature difference in per Kelvin or in per degree Celsius, it doesn't make a difference. So both of these cancel out. And then if I just think about these units, so there's a meter cube here. I can't obviously simplify this further. And pressure is force over area. So Newton over meter square, right? So with that, I see the meters also cancel out with a Newton meter here and a joule on the bottom. So Newton meter is just the unit for work, right? So joules over joules, they cancel out, and this has no units at all, right? And if you are lucky tomorrow, maybe you'll get an easier one for analyzing the units, but again, do not spend too much time on it, right? So yeah, just be wise with your time management. Then it's the percentage uncertainty in y. You get this from the formula which you use to calculate y. So it's a percentage uncertainty in the gradient plus the percentage uncertainty in p. Obviously, there's no percentage uncertainty in k. So you just do this, and without fail, the last part is always you using the equation which is given in the initial parts to calculate something. Because now you have all the constants, so you need to find theta, right? So that's what we do. So for example, if I show you what I did here, is I just made theta the subject of this equation. So it would be PV over YK minus Z. That's what I just did here. Let me write it as well. So this is just PV over YK minus Z, all of which I found. So I just substitute values, right? So yeah. So that's question number 2, right? Let me also show you this question number 2, and let's see if there was something special here. So this was the case where we had ln values. We talked about how we deal with ln's. All right. So that's how we do this. And then everything else is the same. All right. So I just want to get done with question number 2 so that we don't have to come back to it later. And then we can just have a look at question number 1. All right. So for example, let's have a look at this question number 1. How did you get the error bars in this one? It's exactly the same way. It's nothing different here. Are you asking about this one? Again, this is ln, right? So it's max minus min, right? Max minus min is what you have to do for ln. All right, let's go here and have a look at this one. And this is summer 2020, paper 52 in March. Was it summer? So it's March 2020, paper 52. In March, you just have that one variant. So have a look at this, and then we'll just quickly go through how you would write a solution to this. So the bar magnet is displaced a distance at x from its equilibrium position and release. It oscillates vertically. Student investigates how the maximum induced EMF in a coil placed below the magnet depends on x. It is suggested that the relationship between E and x is given by this equation. So all of this stuff is given. You are to investigate a relationship between E and x, right? So what's x? X is how much you displace it. So I guess everybody here can identify that you vary x. This is your independent variable, and you measure E. That's your dependent variable. Everything which is not a constant or one of these primary variables is all going to be your control variables. So for example, this says Ex and alpha, right? Ex and alpha. Whatever you don't see here in these two lines is your control variable. So B, magnetic flux density, N, number of turns, K, spring constant, M, mass of the magnet, all of these will be your constants. A lot of the times, if you've also looked at mark schemes, for the main part, it just asks for one control variable. And then another one, it's given as an additional detail mark. So just score all of these here. So if you do this correctly, you get 4 marks just in correctly defining the problem, right? So that's the first one. So you say keep B constant, keep M constant, keep N constant, keep K constant. So you get all of these marks. All right. So the next one, what's next? So the circuit diagram. Again, do label things that have already been labeled by the examiner as well. So you have the spring, you have the bar magnet, and you have to displace it at distance x. So I guess all of you can also identify the need for a clamped meter rule here, right? To see how much we displace it. So there must be a clamped meter rule. So we can see how much it is displaced. What else? What else? What else? Yeah, so that's what we have to measure the max induced EMF. Right, so this is the max induced EMF. It's not just the induced EMF, it's max, and for good reason. You know this is because this voltage reading is going to fluctuate. That's what it means. So my instrument of choice here would be an oscilloscope, right? And also, if you think about it, if the examiner in this case was also accepting answers as voltmeter, a voltmeter would also work. I would still write an oscilloscope. Do you know why? Because it's very easy to score additional detail marks when you're talking about an oscilloscope. You can talk about the Y gain and all of that stuff, and that gives you marks, right? So that's how you go forward with this reasoning. No, again, it's displaced. It's not like we're providing a frequency consistently. It's just displaced and then released. So no vibrators or signal generators needed here. All right. So then, yeah. So for E, I am going to use a oscilloscope here. And then once you've also, again, let me just write down my thinking, how my thinking goes. Is first I've done planning, right? And I've also talked about how I do the planning stuff. How do I identify the control variables? Next, I do the diagram. The third thing I think about is measurements. What and how do we measure in this equation, right? So everything that you see in this equation, you will need to measure. You will need to measure E, you will need to measure the B, N, X, K, M. Alpha gets a pass because it's a constant, right? So for B, what do you do? Magnetic flux density. Again, this is where you can score a lot of marks. You know that for measuring B, we use a Hall probe. And for Hall probes, you can always get some of these additional detail marks. You can say that you calibrate the probe according to some voltage reading, right? You can also always say rotate the Hall probe until you get a max reading. You can also always say that place it perpendicular to the field, right? So it's plane, the plane of the Hall probe must be perpendicular to the field. These are always points that you can write, and these will earn you marks, right? So yeah, so this is me thinking about B. Then let's think about number of turns. Again, this is not really difficult. You just count the number of turns. So it's nothing special here. How about X? X is the displacement, how much it's displaced. Again, for X, I can also say, where did X go? Yeah, so for X, I can also say that it's if my meter rule is placed so that the zero is at the top and then it reads downwards. So I can say the final reading minus the initial reading. So final minus initial length readings. This is my displacements. K, the spring constant. Again, for a spring constant, I can detail another experiment about how to measure the spring constant. So you apply forces, you measure the extensions. So everything you can talk about in the spring constant, that's also going to earn you marks here. Mass of the magnet, pretty straightforward. You just use a balance to get the mass of the magnet, right? Why would we use a Hall probe? Because that's what we use to measure magnetic flux densities, basically magnetic field strengths. We always measure using Hall probes. All right. So yeah, we use a signal generator or a AC supply in cases where we want to supply not a constant voltage, where we want to supply a, for example, we want to supply an alternating current, right? So then there we would use a signal generator. All right. So this is measuring. At this point, it's also worth thinking about another thing. It's kind of like an unofficial point here. What can maximize our dependent variable? Maybe it's not applicable all the time, but it is applicable most of the times and it will get you marks. So for example, if I look at this expression here, right? So if I want my E, this induced EMF to be as large as possible, what should I do? You guys obviously see we should have a large value of B, so we should have a strong magnetic flux density. We should have more number of turns, right? We should displace it from more distances. We should use a high spring constant spring, and we should have a smaller mass of the magnet, right? So if you write any or some of these, you will also earn some marks here. All right. No, you don't have to draw a Hall probe being used. You don't have to do that. If you've written it, you don't have to do that. All right, so this is all of my measurements part. Now with measurements, I also think about the idea of repeating readings. Can I repeat readings here? So with repeating readings, the idea here is that it's probably not very wise to average here because you'll have different x's each time. But what you can do is, no, sorry. It is actually a good idea to repeat here because for the same displacements that you give, you can find out what the E's are each time. So repeating readings is also something you must be thinking about that at this point, right? Anything related to averaging, repeating readings, you can talk about here. Hmm. So yeah, that's like a pretty good enough explanation regarding this. Uh, some things you just also they are context dependent. So for example, so for the spring constant, you would say that to ensure that this is not deformed, you should not use a very heavy magnet. It also helps make the E large as possible, and it also prevents permanent deformation of the spring. So that's some stuff you can say, right? So yeah, once you've talked about this, so all of this measurements part is done. That's when you go on to the graphing part. So for the graph, this is the relationship. Again, here it's really straightforward if you look. Lower the thickness. Where's the thickness here? There is no thickness here. No thickness here. Are you talking about a Hall probe? No. The Hall probe is just a manufactured thing, a manufactured device that you have on your hands. It's not wise to mess with it right when you're doing this experiment. All right, so yeah, let's think about this now. So let's take this to go. Again, I'm doing this linear law relationship analysis once again for people who are having problems with this. Again, you should not be having problems, honestly. But still, so this is E, right? My independent variable. X is my dependent variable. Also, there's no such hard and fast rule that your dependent variable should always be on the Y, independent should always be on the X. There is no such requirement. Your graph should just be a straight line. So it must be in some straight line form, Y equals mx plus c. So right here, this is my Y. This is my X. And everything here is my gradient, right? So this is M. Now, very obviously, there is nothing else here. So basically, my y-intercept is 0 in this case, right? So what I'll say here is plot a graph of E versus X. And then you should say a straight line. Now, a lot of the times this does not happen. But in this case, it will happen that this straight line should pass through the origin, right? So a straight line passing through the origin is obtained the straight line passing through the origin is obtained if the relationship is valid. Also, something else that you will find in almost every examiner report, the examiner sort of criticizing the students on this, is even the ones that do identify what the gradient is, they often leave it at that. So some people would just be tempted to write this. So alpha b n root k over m, and then just, this is not where it ends. If you look at your expression here, the constant alpha is what you want to find. So this should be the subject of the final equation, not the gradient. So from here, what you should then do is make alpha the subject, right? So this becomes the gradient times. Now it's up to you if you don't want to do it like this. It's not really a problem because this was division by root k over m. It just becomes multiplication by the reciprocal. right? And division by Bn. If you also wrote it as gradient over root k over m Bn, you would still get the mark, right? So that's it then. And then towards the end, you can again write about safety precautions and whatnot. So with the safety precautions, for example, if I look here, so again, this is the case where there could be an instance where the bar magnet could fall off from the spring. So in this case, what I would then say is you use a sandbox to catch the falling magnet, right? So yeah, that's what you can say here. All right. So that's one of these questions. If you guys have anything else you want to ask, go ahead. Regarding calibration of the Hall probe, you just need to say that you should have a calibrate the Hall probe with a known voltage, right? So calibrate the Hall probe. Again, let me write the statement here for you. So calibrate with a known magnetic field. Right? Because in your P4s, you will have studied this idea that the Hall voltage is proportional to B, right? So once you know what the Hall voltage is supposed to be in a known magnetic field, then you can basically use that direct proportion, that unitary method to figure out VH. Can you explain the oscilloscope as in the Y gain? Sure. So with the oscilloscope, just these two formulas that you really need to know. So the amplitude is the Y gain times vertical divisions, right? And the time period is the time base times horizontal divisions. That's just a formula that you need to, the examiner just needs to see this in the cases where you do have to write about a oscilloscope, right? So think about it like this, that if you have a graph shape like this, so you know the amplitude is this, so it corresponds to the vertical divisions. The time period is this, so it corresponds to the horizontal divisions. That's all the examiner wants to see. What else, guys? Anything else? We would use an oscilloscope in this because this asks for the max induced EMF. It's not just asking for the EMF, it's the max one. Right? And you also know this, Rania, that if this bar magnet is going to fall through a coil, it's going to be cutting through those field lines every now and then. So it's going to be leading to some range of values of the EMF. If it's asking for the max, then I'll look at the oscilloscope and look at the max. It's probably going to be late. I'll try to do it, but processing this sort of takes some time. I'm still waiting on my O levels recording, which happened the hour before this one. Just a second. I just made the diagram. Did you just join? I said that the diagram would be basically this, but with a clamped meter rule by the side to measure the displacement, right? And with the coil basically. So you'll have the coil which is placed beneath here, right? And to this coil would be connected the oscilloscope. Again, you want to draw the diagram, you want to draw the circuit symbol, it's up to you. You don't want to draw it, again, your call. As long as everything is labeled clearly, because it does mention a coil. And then to the side, you'll have a clamped meter rule through which you'll be taking the X readings as to how far it's displaced. No, you're not supposed to revise any of the theory stuff. If you do know the theory stuff in question number 2, it just gives you some certainty as to whether you're doing it correctly or not, right? So I was just the other day doing that question related to capacitances. So because I know that my TOR turned out to be in seconds, so I'm just certain with my calculations that all right, I'm doing something correctly. But you, strictly speaking, don't need to know it. You don't need to. All right, guys. Anything else? Could you summarize the use of light gates? I don't really want to talk about it. I generally refrain from using light gates because with light gates have to be mentioned really precisely in your explanation as to what you want to measure. For example, let's say that this magnet falls through. If I want to measure its instantaneous speed, then the light gate should be positioned like this, that with the light gates here, we would just measure the time that it takes for it to fall through, and I measure this distance, right? So this gives me the instantaneous speed basically of this bar magnet as it falls through. So you just say that as one ray of light is cut, the timer starts. So basically when this end, let's draw it like this here. So when this end passes here, so this ray of light, when this is cut, the magnet starts timing. And when the top end passes, so the timer stops. So then if you have this length, of the bar magnet, you can divide this by the time that you get from the oscilloscope. That's going to give you its speed just as it passes through. I find it a bit complicated as far as students go, and as far as my teaching experience tells, students do tend to find this complicated, and there's no such hard and fast rule of using a light gate. You can also just use a good old stopwatch and write out your response. So you do need to mention what length this is. This is what people have troubles with. So that's why I generally avoid using this. How to use a signal generator? You just connect the signal generator, and then you say that I give it sort of this sort of frequency and that sort of a thing. You don't really have to know its use. You should just know that it's used for cases where you want to supply an alternating voltage or an alternating current. Analysis of data part. This is this what we're talking about? Okay. Anything else, guys? You don't. You don't. Questions related to that will never come. Barometer, just by the way, for general knowledge, barometer is used for measuring atmospheric pressure, and manometer is used for measuring the pressure of a gas supply, for example. What else, guys? Yeah, you can basically, it has knobs, and you can change it to whatever setting you want to supply. No, I have absolutely zero guesses on P5, and any half decent teacher would also tell you the same. It's just really senseless to guess on P5. I mean, there is no such pattern. So yeah, and you guys also, obviously, if any good student also, Rania, what sort of question is this? Any good student would also never ask for a pattern on P5. There are just some skills that you want to use for each of those questions, right? So that's not a good question. Do we have to specify the maximum count of each apparatus being used? No, you don't. Yeah, I know. P4 predictions were very nice. Also, I wanted to write something out, but that was a day when your class ended, I had been teaching for 6 hours straight and I was totally drained. I wanted to do something, but then all I managed to do was just download the recording and upload it, which also I surprised myself having enough energy to do that. But I'm glad that you guys had such a good P4. Uh, yeah, I'm really happy. All right, amazing guys, amazing. That's nice to hear. Amazing. Inshallah, P5 will also it will also go well as long as you stick to this stuff. P5 is really simple. I mean, as long as you know some basic steps, it's the same thing over and over again. If you learn by doing, then maybe even like tonight, if you do like 3 papers or maybe like 5 or 6 papers, you can still do P5s from scratch. Photocells and rheostats. Usman, where are you getting this from? Photocells are never asked in any sort of planning question. Rheostat is just a variable resistor, and you should think of this. You should think of this whenever, for example, the examiner wants you to change the current. No, Z nodes is outdated. It was good once upon a time, but it's outdated now. I don't really recommend it. Don't look at it, Usman. Look at a question. Look at different papers P1s. Look at those and then ask questions about any of those if that's a problem. All right. Okay, guys. So yeah, let's end this now. So this get processed in time so that I can also upload it on YouTube. So yeah, best of luck. Inshallah, it will be very nice. P5, I've rarely ever heard of there being a difficult P5 as such. But yeah, not really. You should just know, Osman, when you use what sort of a length measurement instrument, right? So, for example, diameter of a really thin wire, I would use a micrometer. Maybe if that length is slightly larger, I would probably use a vernier caliper. But the special use case of a vernier caliper is when I want to take some internal measurements. So, for example, if I have this cap of a bottle, right? I can take the external measurements. Now, this one doesn't seem like it has a lot of thickness. But if it did have some thickness, and if I wanted to take the internal diameter here, in that case, I would use a vernier caliper, nothing else. With anything that you want to talk about micrometers and vernier calipers, do mention this thing that you take the readings. For example, if this is your thing that you want to measure the diameter of, so you take it along different positions and then average out the diameter. Again, only use signal generators, or again, don't even use this word if you don't like it. Just say an AC supply. Whenever you want to supply an alternating current or a voltage, we use an AC supply. All right. That good enough for you? Yes, Rania, AS classes now at 7. I'll just pray and yeah. All right, guys. So best of luck. So yeah, I'm really hopeful. If P4 was that nice, so P5 would also probably be amazing. Just don't be overconfident. Do have a look at the time management, right? Aim to get done with it as quickly as possible. Some people like to get started with question number 2 first. I never really understood it, but if you feel like that helps you, you can also do that. All right. In an AC supply, how will we measure frequency? Again, an oscilloscope. You use a time-based setting, you find the time period, and then you reciprocal it for frequency. Yes, guys, please, let's end here. If you have any more questions, just ask on the platform. I'm asking this, I'm only doing this because I want to get this processed in time for me to later upload. Yes, Usman, love you too. And best of luck for tomorrow. So guys, all right, let's end this here. And if you have any more questions, just ask on the platform. I'll do my best to get this uploaded on YouTube within an hour. All right. Best of luck, guys. Allah Hafiz.